Until now, in 229, we have on purpose simplified the abstraction of memory. We have said that memory is essentially an array of bytes and that we address memory by giving the number of the byte that we want to access. So the memory address of a word, for example, is the number of the byte or the position of the byte in this array for the first byte of that word. And we have separated the data that we manipulate as either being memory or being registers. Now it's the time for us to look at the concept of memory hierarchy, that is the organization of data storage in an actual computer. And we'll see that there is more complexity to memory storage or to data storage than simply imagining the memory as being a single linear array of bytes. To understand where this complexity comes from, we need to look at different memory technology or different data storage technology. One of the technologies that we need to consider are SRAM, that stands for static RAM, and the static random access memory is a memory where as long as I provide energy to the device, the data will remain stable in the device indefinitely. While in a dynamic random access memory, I may store data to a cell and I may keep providing power to that memory device, but if I don't do anything, if I don't do something called refreshing, the data may disappear. So we're going to understand much better about these technologies when we get to the lecture about memory technology. But for now, what is important to us is to consider, for example, the typical access time for these different types of memory and also the cost per gigabyte for the different memory technologies. And I have two price points here in 2008 and in 2020. So look at the data in this table. The typical access time for an SRAM will be between 0.5 and 2.5 nanoseconds, depend on the technology that you're looking at. While the typical access time for a dynamic RAM will be between 50 and 70 nanoseconds. To put that in perspective, let's recall that if I have a moderate speed processor that's running at a clock of 2 gigahertz, the clock cycle will be 0.5 nanoseconds. So if I consider a clock cycle of 0.5 nanoseconds and the access to my DRAM takes between 50 and 70 nanoseconds, that means that accessing an item in memory will take between 100 and 140 clock cycles. So consider that in the model that we have so far for the execution of a program in our RISC-V processor, we have to access the memory to fetch an instruction for every instruction execution. And if it's a load or store, we need to access memory to fetch data or to store data. If we had to wait 140 clock cycles for each one of those operations, each instruction would take a minimum of 140 cycles, perhaps 280 cycles for instructions that access memory. Obviously, that could not work because we put so much effort on improving the design of the processor and pipelining the execution so that we could reduce the clock cycle. And we spent lots of time worrying about, for example, load use data dependencies and branch prediction to reduce the number of idle cycles. So we need to do something about that. But now, if we look at storage drivers, an access to any storage driver can take anything between 5 million and 20 million nanoseconds. If I look at the cost per gigabyte of for a gigabyte of SRAM in 2008 was between $2,000 and $5,000. For DRAM was between $20 and $75. And for storage drivers, it was between 20 cents and $2. I just looked today at the prices for 2020, And the SRAM price has been reduced to about $1,000 and $1,250 per gigabyte. The cost of a DRAM has dropped to about $3 per gigabyte. And the storage drivers, if I look at an SSD for 1 terabyte, I could buy it for $80, which would give me a cost of 0.0880 cents per gigabyte. So as you can see, the cost of both the DRAM and the storage drives has been dropping significantly. The cost of an SRAM, gigabyte of SRAM, has not dropped as much as for these other devices. So what kind of memory would we want in our computer? Ideally, in our computer, we would like to have a memory that has the access time of an SRAM and the cost per gigabyte of a storage driver. Can we have that? No, we can't. We cannot have that exactly, but we can design a system that will emulate a memory that will be very fast, perhaps in the best cases as fast as an SRAM, and that will be relatively cheap, not as cheap as a memory that's created entirely by storage drive, but considering the entire data capacity that I need for my system, it will be close to that. How do we do that? How do we build such a memory system? So the SSD access time is between 35 and 100 microseconds, but that is 35 to 100,000 nanoseconds. So here I have a plot for the historical price of DRAM. Unfortunately, this plot only goes until 2015, and I went back to the website, and there's no updates after that. But what I can see is that if I look at this graph, this will show in these early years here, from between 1955 and about 1970, there are some types of memories that are no longer in existence today. So if you want to look at current trends, we can look at the small drives memory price down here. And here we can see the prices for flash memories, and this is the price for DRAMs. So you can see that there is, over time, there is oscillation in prices, but the trend for all those prices is to drop. So how do we build a memory that is very fast, but doesn't cost as much? And there is another aspect to memory, that the SRAM consume the most energy per byte that's stored of the three technologies. So if we were to build a system entirely with SRAMs so that it can be fast, it would consume lots of energy and it would be extremely costly. We cannot do that. So we wanted to create a system that can emulate the speed of an SRAM and have the capacity of the combination of DRAM and storage drivers. So what we're going to use is the principle of locality. The principle of locality is based on the fact that programs access a small portion of their address space at any time. So there are two aspects to locality. There is temporal locality. The temporal locality says that items that I have accessed recently are likely to be accessed again soon. So there is locality in time. If I access something now, I am likely to access the very same thing again in the near future. So this we call temporal locality. For example, if I am executing a loop where I execute instructions in a loop, it is very, what will going to happen is that I will access a few instructions. You have written many different loops in your assignments, and often your loops will have 15, 20, 25 instructions. And I'll be executing those very same instructions perhaps millions of times. So I'm going to be accessing the very same instructions again in the near future. Another example are the induction variables in a loop. So if I have a for I code, for example, I will be incrementing the variable I in every iteration of the loop. So I have to load the value of variable I and then start the variable I in every iteration of the loop. When I access web pages, I have a tendency of going back to the same web pages that I have accessed recently. So there is, in all computing, there is this phenomenon that things that I access right now, I am very likely to access again in the near future. We call this temporal locality. There is another locality that another type of locality that's called spatial locality. Spatial locality says that items that are near those that I accessed recently are likely to be accessed soon. So in the case of the loop, for example, as if I access one of the instructions in the loop, it's very likely that I am going to execute instructions that are nearby that instruction in the near future. The same thing with data stored in memory. For example, if I traverse in an array, I access one element of the array, I am very likely to access elements of the array that are nearby in the near future. So those are two examples of spatial locality. So that we can better understand locality, I create a graphic representation for locality for this lecture. So here is the idea of temporal locality. So we are all by now familiar with memory, and this is our representation on the slide of memory. And in this case, each one of those boxes represent a word. So, and here is time. And the idea here is that as time passes, I will be doing access to different locations in memory. So perhaps at this time, I access this location, and then in the near future, I am likely to access the very same location again. This is what we call temporal locality. I go back to the same place that I have been in the recent past. So the same location is accessed several times in a relatively small interval of time. Spatial locality is different. Spatial locality says that if I access a given location in memory now, it's likely that in the near future I'm going to access other locations in memory that are close to the one that I just accessed. So this is the idea of spatial locality. So locations that are close to each other are accessed within a short interval of time. So what we're going to do to build our memory that has a fast access time but has a cost that's much lower, we're going to take advantage of that the principle of locality. And for that, we're going to build a memory hierarchy. So everything, code and data, is stored initially in solid state drives. So remember, the solid state drives are cheap, they can have a high capacity, and the cost per byte to store in those devices is very low. And then what I'm going to do, I will copy recently accessed items from the drives into smaller DRAM memory that I call main memory. So I'm going to be copying from these drives that have high capacity, low energy, and low cost into the DRAMs that is my main memory. And then I will copy the more recently accessed items and the items that are near the more recently accessed item into the even smaller SRAM memories that are very fast. And these SRAM memories I will call cache, and the cache memories are attached to the CPU. So in a typical design, the cache memory is built inside the same chip as the processor, so that it can be very close by and I can access the cache memory very fast. Now, if we go back to the example of executing our loop that may have 15, 20, 30 instructions, if all those instructions fit in my cache memory that's inside my processor, I only gonna be going to the main memory to access those instructions in the beginning, in the first execution of the first time through the loop, and I'll keep a copy of all those instructions in my cache memory. When I go the second time around to execute the loop, I have already those instructions in the cache inside the processor, and I don't need to go back to DRAM or to the drivers to get the data. So here is an example of a simple program. This program computes the sum of the product of matrix AI and BI. So in this program, I will start by initialize the variable sum to 0. And then I will initialize the variable I to 0. And I will create the value of n in some register. And then I will multiply the value of I by 4, because this is an access to arrays that I assume are integers. And then I'll do all my accesses inside the loop. And then I'll test whether I is less than n, and I'll go back to the beginning of the loop. So in this case, you can see that I have a spatial locality because I'm executing the instructions sequentially. And I have temporal locality because if my loop, and in this case is a very short loop because I'm going to be loading the value of A, the value of B, and adding to the sum. So I have very few instructions in the loop. So once I execute this shift left logical immediate instruction, I'm going to execute a few instructions and I'll go back and execute the very same instruction again. So I'm going to have significant temporal locality while executing the loop. So I have, this is the sum I have the base of I, and I have the base of B. This is the layout of my data in memory. And then I have the positions of the array A0 and the positions of array array A sub I and B sub I, and that will be stored in this fashion. So I'll have temporal locality to access the base of the array because I'll be accessing the base of the array in every iteration of the loop. And I'll have spatial locality as I access the elements of the array, because once I access the element 0 of the array A, I will in the near future access the elements 1, 2, and 3, similar to array B. So that's how I'm going to take advantage of my spatial and temporal locality, and this is a concrete example to illustrate how they occur in the execution of a program. So there are several levels in the memory hierarchy. I have the processor, and close to the processor I have small memories that are fast, and as I get farther away from the processor, I have larger memories that are slower. I will have to transfer data in between these different levels of the memory. So we're going to define a block as the unit of copying between two levels in the hierarchy. A block may be multiple words. I don't transfer single words between these memory levels, between these different levels in the hierarchy. Most typically, I'll be transferring multiple words every time that I move data in between them. If the data is present in the upper level in the hierarchy, then I say that the access was a hit. The access was satisfied by the upper level in the hierarchy. And then I can define the concept of a hit ratio, that is the number of hits divided by the number of accesses. So the hit ratio tells me how often I needed a piece of data and I found that piece of data at the higher level in the hierarchy. If the data is not in the upper level of the hierarchy, then I have a miss. A miss occurs when the block has to be copied from the lower level to the upper level because it was not in the upper level when it was requested by the processor. The time taken to bring that block of data from the lower level to the upper level is called the miss penalty. and I can compute the miss ratio as the number of misses divided by the number of access. So the miss ratio tells me how often I needed a piece of data and I could not find it in the upper level of the hierarchy. The miss ratio is 1 minus the hit ratio. After copying from the lower level, the data is supplied to the upper level, the data is supplied from the upper level to the processor, for example. And the data is retained in the upper level until a time where there is no more space in the upper level, and then we're going to have to remove some data from the upper level. And in the subsequent lectures, we're going to understand how we do these replacements and what are the policies that we use to make such replacements.